Welcome to our exploration of motion in a straight line, a fundamental concept in physics. In this chapter, we'll break down what it means for an object to move in one dimension, discuss key terms like position, displacement, speed, and velocity, and see how these ideas form the basis for understanding more complex motion. Whether you're new to physics or brushing up on the basics, this journey will help you grasp the essential principles that govern how objects move along a straight path. Let's begin by defining motion in one dimension and why it's so important. Motion in one dimension, also known as linear motion, refers to the movement of an object along a straight path. In this type of motion, the object's position changes with respect to time, but only in a single direction. This simplifies the analysis, as we only need to consider movement along one axis, typically the x-axis. Understanding motion in one dimension lays the groundwork for studying more complex motions in two or three dimensions. It's the perfect starting point for building your physics knowledge. Let's talk about position and displacement. Position describes the location of an object at a particular moment, usually measured from a reference point. Displacement, on the other hand, is the change in position of the object. It's a vector quantity, meaning it has both magnitude and direction. For example, if you walk 5 meters east from your starting point, your displacement is 5 meters east. Understanding these concepts is crucial for analyzing how objects move. Now let's differentiate between distance and displacement. Distance is the total length of the path traveled by an object regardless of direction. It's always a positive value and is a scalar quantity. Displacement, as we discussed, is the shortest straight line distance from the initial to the final position, and it can be positive, negative, or zero depending on direction. This distinction helps us understand not just how far an object moves, but also in which direction. Speed and velocity are two terms often used interchangeably, but they have distinct meanings in physics. Speed is the rate at which an object covers distance, and it's a scalar quantity, meaning it has magnitude only. Velocity, however, is the rate of change of displacement and is a vector quantity, so it includes both magnitude and direction. For example, if you drive 60 km/h east, your speed is 60 km/h, but your velocity is 60 km/h east. Average velocity gives us an overall idea of how fast and in what direction an object moves over a period of time. It's calculated by dividing the total displacement by the total time taken. Unlike average speed, which uses total distance, average velocity considers only the straight line change in position. This makes it especially useful for understanding motion that changes direction or involves returning to the starting point. Instantaneous velocity is the velocity of an object at a specific moment in time. Imagine looking at a speedometer in a car that's showing you the instantaneous speed, and if you know the direction, you have the instantaneous velocity. It's determined by taking the limit of the average velocity as the time interval approaches zero. This concept is crucial for analyzing motion at any given instant, especially when speed or direction changes frequently. Acceleration measures how quickly an object's velocity changes over time. It's a vector quantity, so it includes both magnitude and direction. If an object speeds up, slows down, or changes direction, it's experiencing acceleration. For example, when a car starts moving from rest or comes to a stop, it's accelerating. Understanding acceleration helps us predict and describe changes in motion. Acceleration can be uniform or non-uniform. Uniform acceleration means the velocity of an object changes by equal amounts in equal intervals of time. Think of a car steadily increasing its speed. Non-uniform acceleration, on the other hand, means the rate of change of velocity varies over time, like a car stuck in stop-and-go traffic. Recognizing the difference helps us choose the right equations and methods to analyze motion. An acceleration is constant. We can use a set of equations called the equations of motion to predict an object's future position and velocity. These equations relate displacement, initial velocity, final velocity, acceleration, and time. They are powerful tools for solving a wide range of problems in physics, from simple straight-line motion to more complex scenarios. Let's derive the first equation of motion, v equals u plus at. Here, v is the final velocity, u is the initial velocity, a is acceleration, and t is time. This equation tells us how the velocity of an object changes over time when acceleration is constant. By understanding this relationship, we can predict how fast an object will be moving after a certain period. Now let's derive the second equation of motion, s equals up plus 1 to it 2. In this equation, s is displacement, u is initial velocity, a is acceleration, and t is time. This formula helps us calculate how far an object travels under constant acceleration, starting from an initial velocity. It's especially useful for analyzing objects in free fall or vehicles accelerating along a straight road. Third equation of motion is v2 equals u2 plus 2 as. Here, v is final velocity, u is initial velocity, a is acceleration, and s is displacement. This equation is particularly helpful when you need to relate velocity and displacement without knowing the time. It's widely used in problems involving stopping distances and projectile motion. Free fall describes the motion of an object under the influence of gravity alone with no other forces acting on it. When an object is in free fall, it accelerates downward at a constant rate, known as the acceleration due to gravity. This concept is key to understanding how objects move when dropped or thrown vertically. Equations of motion we've discussed can be adapted for free fall by replacing acceleration with the acceleration due to gravity, usually denoted as g. For example, the equation v equals u plus at becomes v equals u plus gt. These equations allow us to predict how fast an object will be moving or how far it will fall after a certain time. Graphs are powerful tools for visualizing motion. By plotting position, velocity, or acceleration against time, we can quickly see how an object's motion changes. These visual representations help us interpret data, identify patterns, and make predictions about future motion. Let's explore the different types of motion graphs. Position time graph shows how an object's position changes over time. The slope of the graph represents the object's velocity. A straight, sloped line indicates constant velocity while a curved line shows changing velocity. By analyzing the shape of the graph, we can determine whether the object is moving at a steady pace, speeding up, or slowing down. Velocity time graph displays how an object's velocity changes with time. The slope of this graph represents acceleration. A straight, horizontal line means constant velocity, while a sloped line indicates constant acceleration. The area under the curve gives us the displacement, making this graph a valuable tool for analyzing motion. Acceleration time graph shows how acceleration varies over time. A horizontal line indicates constant acceleration, while a line above or below the time axis shows positive or negative acceleration. By studying this graph, we can quickly identify periods of speeding up or slowing down and understand the overall motion of the object. Graphs aren't just for visualization, they can also be used for calculations. For example, the area under a velocity time graph gives the displacement of an object. This method is especially useful when dealing with irregular motion where equations alone might not be enough. Understanding how to extract information from graphs is a key skill in physics. You might wonder why we focus so much on motion in a straight line. The answer is that it forms the foundation for all motion analysis in physics. By mastering these concepts, you'll be better equipped to tackle more complex scenarios, such as motion in 2 or 3 dimensions, circular motion, and even the motion of planets. It's the starting point for understanding the universe's laws. Every measurement of position or displacement starts with a reference point. This is a fixed location from which all other positions are measured. Choosing the right reference point is essential for clarity and accuracy in describing motion. For example, your home might be your reference point when describing your journey to school. In physics, quantities are classified as scalars or vectors. Scalars have only magnitude, like distance or speed. Vectors have both magnitude and direction, like displacement or velocity. This distinction is important because it affects how we add, subtract, and interpret these quantities in motion analysis. Direction plays a crucial role in motion. For vectors like displacement and velocity, specifying direction is as important as stating the magnitude. In one-dimensional motion, we often use positive and negative signs to indicate direction along a straight line, such as east or west or up and down. Accurate measurement is the backbone of physics. For motion in a straight line, we use standard units: meters m for distance and displacement, meters per second ms for speed and velocity, and meters per second squared ms2 for acceleration. Using consistent units ensures clear communication and reliable calculations. In one-dimensional motion, negative values often indicate direction. For example, a negative velocity means the object is moving in the opposite direction to the chosen positive axis. This use of signs helps us describe motion more precisely, especially when objects reverse direction. Instantaneous speed is the magnitude of instantaneous velocity. It tells us how fast an object is moving at a particular instant without regard to direction. This is what a car's speedometer shows. It's always a positive value and is useful for real-time analysis of motion. When an object's velocity is 0, it's at rest. This means there's no change in its position over time. Understanding rest is important because it serves as a reference for analyzing when and how objects start or stop moving. Uniform motion occurs when an object moves at a constant velocity, covering equal distances in equal intervals of time. There's no change in speed or direction. This type of motion is the simplest to analyze and forms the basis for understanding more complex movements. Non-uniform motion means the object's velocity is changing, either in magnitude, direction, or both. This could be due to speeding up, slowing down, or changing direction. Analyzing non-uniform motion requires more advanced tools like acceleration and the equations of motion. Reading and interpreting motion graphs is a vital skill. By examining the slopes and areas under curves, we can extract valuable information about an object's speed, velocity, acceleration, and displacement. Practice with different types of graphs will make you more confident in analyzing real-world motion. Imagine a car driving along a straight road. By tracking its position at different times, we can plot a position time graph. If the car speeds up, slows down, or stops, these changes will appear as different slopes or curves on the graph. This real-world example helps connect theory to everyday experiences. Consider dropping a ball from a certain height. The ball accelerates downward due to gravity, and its motion can be analyzed using the equations for free fall. By measuring how far it falls over time, we can calculate its velocity and acceleration at any point during the drop. Picture a runner sprinting along a straight track. By recording the runner's position at regular intervals, we can analyze their speed, velocity, and acceleration. This example demonstrates how the concepts of motion in a straight line apply to sports and athletics. It's easy to mix up distance and displacement or speed and velocity. Remember, distance and speed are scalars while displacement and velocity are vectors. Always pay attention to direction and use the correct equations for the situation. Careful analysis prevents errors and leads to accurate results. To solve motion problems, start by identifying what's given and what you need to find. Choose the appropriate equation of motion, substitute the known values, and solve for the unknown. Drawing diagrams and graphs can also help visualize the problem and organize your work. Always check your units and make sure your answers make sense. For example, if you calculate a velocity, the unit should be meters per second, ms. If your answer seems unreasonable, double-check your calculations and reasoning. This habit ensures accuracy and builds confidence in your problem-solving skills. Let's recap the key concepts. Motion in a straight line involves position, displacement, distance, speed, velocity, and acceleration. We use equations of motion for constant acceleration and analyze motion with graphs. Understanding these basics prepares you for more advanced topics in physics. The principles of straight-line motion are everywhere, from cars on highways to athletes on tracks and objects in free fall. Recognizing these patterns in daily life not only deepens your understanding of physics, but also shows the practical value of what you're learning. Mastering motion in a straight line sets the stage for more advanced studies like motion in 2 and 3 dimensions, circular motion, and dynamics. With a solid foundation, you'll find it easier to tackle these challenging topics and see how they connect to the world around you. The best way to master these concepts is through practice. Work on a variety of problems, draw graphs, and experiment with real-life examples. Each problem you solve strengthens your understanding and prepares you for more complex challenges in physics. Modern technology like motion sensors and data analysis software makes it easier to study and visualize motion. These tools allow for precise measurements and instant graphing, helping you see the principles of motion in action. Embracing technology enhances your learning experience. In equations and graphs, we use standard symbols: S for displacement, U for initial velocity, V for final velocity, A for acceleration, T for time, and G for acceleration due to gravity. Familiarity with these symbols makes it easier to read and solve physics problems. Stay organized, keep practicing, and don't hesitate to revisit the basics if you're unsure. Drawing diagrams, labeling axes, and writing out steps clearly can help you avoid mistakes and build a strong understanding of motion in a straight line. Congratulations on completing this overview of motion in a straight line. With these concepts under your belt, you're ready to explore more complex motions and deepen your understanding of the physical world. Remember, every journey in physics starts with a single straight line.